Hello everyone, my name is Lukas Neukom, and together with Scheller, I will present this highlight talk on semi-supervised machine learning in the context of speech recognition. In this talk, we will give you a short overview of some interesting publications in this area over the last few years. The talk will only discuss the topics on an abstract level and not delve too much into the details, but we will always point you to the original work, so if you are interested, you can read the paper or watch the original presentations. Let's start with the general setting of speech recognition. In this talk, we will focus on end-to-end speech recognition. This means that as an input, we have some kind of audio signal, shown on the top left, and we want to be able to predict its transcript using some sort of model. In contrast to a more traditional pipeline, where the audio is first transcribed to phonemes with a dedicated model and then is translated to text with other models. Our model does everything at once. To train such a model, we need audio files together with their transcripts. Usually, those audio files are between 2 and 12 seconds long, and we don't need a more fine-grained alignment between the audio and the transcripts. For example, we don't need word or character level alignment, which is usually needed for the more traditional pipeline. There are some very well-known corpora for the training of such systems. For example, we have LibriSpeech and the more recent MLS corpora, which are both based on free public domain audiobooks from LibriVox. Both of these corpora were automatically aligned and contain some error. As you can see, LibriSpeech contains around 1,000 hours for English, while MLS contains around 45,000 hours for English and around 2,000 hours for German. We also have Common Voice, which uses another approach to collect data. It's an initiative by Mozilla where they are crowdsourcing an open source dataset of voices. You can help them by either donating your voice or by validating other people's clips. Common Voice has already collected around 800 hours for German and around 1,700 hours for English. But they don't have any data for Swiss German. For Swiss German, there exists no public dataset yet, at least not for Swiss German audio to standard German text. In a previous talk, Michel Plus has already presented some work we did in this area in the last year, where we used a similar approach to LibriSpeech and MLS to create a corpus of around 300 hours. Before we start with semi-supervised methods, let's first shortly introduce the concept of supervised and unsupervised machine learning. In supervised machine learning, we usually have some kind of label for the data. We have already seen one such example in speech recognition, where the transcript is the label. Another example is machine translation. In this problem, we want to translate text in one language to text in another language. In this case, the translation is the label. On the right-hand side, you can see some examples for unsupervised machine learning, where we don't have any kind of labels. In this kind of machine learning, we try to find patterns in the data. For example, in clustering, we try to find groups in the data based on some kind of metric. Another example is language modeling, where we try to learn the structure of language based on text alone. For unsupervised machine learning, it's usually much easier and cheaper to obtain data, since the labeling is usually what makes obtaining data expensive. For example, to create data for speech recognition, we can either transcribe already existing audio, record audio based on existing text, or we can align existing audio and text as we have seen in LibriSpeech and MLS. All of these methods are very time consuming and can be very expensive. But to obtain data for language modeling, we can just scroll the internet and, for example, use the complete Wikipedia for training. This is also the motivation for semi-supervised machine learning. We want to be able to use all the freely available unsupervised training data to help solve machine learning problems such as speech recognition. Concretely, in the case of speech recognition, this means that we want to use audios without any transcript for unsupervised training and somehow improve supervised training of models. In the following, we will present two such approaches, namely noisy student training and self-supervised representation learning. We will start with noisy student training, which is an iterative process first used on ImageNet classification and then adopted by Park et al. For speech recognition. On the top left, we again have our small supervised labeled dataset, which we will use to train an initial model called the teacher model. We will then use this model to predict labels on the large unsupervised dataset on the right. In the next step, we will train a new model called the student model on both supervised and unsupervised datasets. After this, we will make the student a new teacher and repeat this whole process. This means that again we use the teacher to predict labels for the large unsupervised dataset and then train a new student, and so on. The goal of each iteration is that the student is better than its teacher, which might seem counterintuitive since the student learned on the original data the teacher was trained on, and on new data which is based on the teacher. The main feature of noisy student training to make this possible is the use of data augmentation. This means that the teacher produces high-quality labels for unsupervised dataset, while the student has to learn to reproduce those labels with heavily augmented input data. This is a much harder problem and should lead to better generalization of the student. There are multiple tricks used in practice to make this work better. For example, the teacher uses a language model trained separately on large amounts of text data during decoding, which can increase the quality of the labels significantly. The output data is also filtered by removing low confidence example and balanced to match the supervised label distribution. The whole process is repeated for multiple generations and the best model is used for evaluation. In the case of the paper by Park et al., this evaluation was done on LibriSpeech 100 benchmark. This is a semi-supervised task where the clean 100 hours subset of LibriSpeech is used as the supervised training data, and the remaining 860 hours can be used in an unsupervised fashion. In the graph, we can see the resulting word error rates, which means that less is better. They used an LS model, which is a listen, attend, and spell model, with a bidirectional LSTM encoder and an LSTM decoder. They trained the model for 6 noisy student generations, and the initial teacher model, which was only trained on the supervised dataset, is used as a baseline, with a word error rate of 16.9. The best model is the generation 4 model using an external language model. As you can see, they were able to reduce the word error rate from 16.9 to 8.6 using this method. Using no external language model, noisy student training still improved the model to a word error rate of 9.5. But as you can see in both cases, noisy student training reduced the word error rate significantly by only using unsupervised training data.
We are now coming to the second part of this talk, where we look at self-supervised representation learning methods for speech recognition. We again are in the same situation as before, where we have large amounts of unlabeled data, which we want to use to improve our model's performance on a downstream task, of which we only have a small amount of labeled data available. This time, however, our approach is a bit different. An important observation that motivates self-supervised representation learning is that for many tasks, not all information of the high-dimensional input data, like videos or images, is required. For example, if we want to classify dog images, like for example, the image here in the slide, if we want to classify what kind of dog this is, then the background pixels might not hold important information. For example, in this case, the waves in the background and the drops of water in the air, they're not important for the task that we want to solve and might even complicate the task. Now, the idea of self-supervised representation learning methods is to use these large amounts of unlabeled data to train a representation model. This representation model projects high-dimensional input data like images or audio into a lower dimensional representation vector. This representation vector should ideally only contain important information for the task that we want to solve, and irrelevant information should be removed. Having such representation, supervised learning of downstream tasks should become much easier. And to achieve such representation, we here employ self-supervised losses that use labels that come from the data itself. So we have annotated data where no human label is available, and instead we use labels that come from the data itself. Now let's look at two examples of what such loss function might look like. One simple example for such self-supervised loss is predicting image rotation in computer vision. Thereby, input images, like for example the image of the dog here, are first rotated by a random rotation. These rotated images are then fed into a representation model, which correctly must predict the rotation that was applied. For example, in the first row, the representation model should predict 0 degrees because the image wasn't rotated at all. And for the last row, the image was rotated for 270 degrees. So the representation model should predict exactly this value. We then can drop the last layer or the last n layers to get the representation vector. Another family of examples are contrastive losses, like in SimCLR. In the example of SimCLR, input images are first transformed by two randomly sampled transformations, like shown here. And then these transformations are fed into a representation model that produces a representation vector. Now, during training, the model is updated in such a way to maximize the agreement between these two vectors. This way, transformations should motivate the representation model to ignore noise and focus on important information about the class of the image. Now, while this might sound like a good way to go, a major problem remains. With the current setup, their representation model can find very trivial solutions. For example, it could predict the same vector for all inputs, which would clearly maximize the agreement, but it's also clearly not what we wanted to do, and such representations would be useful for a downstream task. Now, to circumvent that, we employ a contrastive loss. This contrastive loss motivates the model to maximize the agreement between output of the same input, as we've seen before, but at the same time minimize the agreement between all other pairs. We therefore require negative samples, which we usually obtain from the same inputs, from the same batch that we are currently training on. As mentioned before, we want to use this learned representation to accelerate our downstream tasks, in our case, the transcription of speech signals. To do so, we fine-tune a task model on top of the learned representation model using the labeled data that we have. The representation model is thereby frozen, and only the usually small task model is updated. We sometimes even have only a linear layer as task model. Self-supervised representation learning combined with supervised fine-tuning has found many successful applications in many domains such as computer vision, natural language processing, or even reinforcement learning. Now, Wave2Vec is an application of this concept to speech data. In Wave2Vec, raw audio inputs, shown here on the bottom, are first transformed by convolutional neural networks to produce intermediate representation vectors here. These vectors are then further transformed by a transformer model to produce the final representation vectors. Now, during training, a fraction of the inputs to the transformer are masked, like shown here, and the contrastive task then is for the transformer to correctly predict the vector here that was masked. Whereas it should maximize the agreement between the true vector and the predicted vector, and minimize the agreement between negative examples, which are drawn from the same training batch. Now, having trained such representation model, we can use it to fine-tune a linear projection head on labeled data. To do so, we again feed training samples, raw training samples of raw audios into the convolutional neural network and transformer models that we have pre-trained to obtain representation vectors, and then transform them with a linear projection to predict the labels that we have here. In this case, transformer and CNN model are, the weights of these models are frozen, and we only update the linear projection head. Now let's see how the performance of this model looks like. Again, we are looking at word error rates on the test set of the LibriSpeech 100/860 benchmark, whereas less word error rate is better. We see that compared to Noisy Student, wave-to-vec requires only 10 minutes to 1 hour of labeled data to achieve similar performance. Having same amount of labeled data, 100 hours here, wave-to-vec clearly outperforms Noisy Student training with a word error rate of 5 compared to 8.6 of Noisy Student. The last bar here in this plot shows that wave-to-vec is able to scale well to large, very large, unannotated speech datasets. For example, in this case, authors used an unlabeled dataset of 50,000 hours of unannotated speech data to pre-train this wave-to-vec model, and then we're able to achieve the same performance as Noisy Student training of 100 hours with only 10 minutes of speech data. For Swiss German to standard German speech to text, currently only a few relatively small labeled datasets exist that are publicly available. However, there are many possible sources for large amounts of unlabeled data. For example, many parliaments record their debates, whereas only a few have actually little transcripts. Also, there are many Swiss German TV and radio shows that could serve as sources for large amounts of annotated Swiss German speech. Applying semi-supervised representation learning methods like Noisy Student training and wave-to-vec, which we have looked at in this talk, to such data is a promising step towards high-quality speech text for Swiss German. Now, to facilitate the development of semi-supervised methods for Swiss German speech to standard German text, there was a shared task on this topic at this year's Swiss Text Conference. The goal thereby was to train Swiss German speech data to Swiss German speech to text systems using large amounts of, in total, 1,208 hours of annotated data and a relatively small amount of 283 hours of annotated data. We are very happy that this year we had many participants with very interesting and innovative approaches. If you weren't able to attend the workshop, you can still read the system descriptions in the proceedings. And now we are already at the end of this talk, and we want to thank you very much for your attention. And now will be the time for a question answering and a discussion. Thank you very much.
Thank you very much. Thank you for the whole team for this interesting presentation. We have still 5-6 minutes to ask questions to Christian. So.
Yeah, hi. I have a question, if I may. So thanks a lot for the presentation. My question is basically, what is the compute comparison for, let's say, noisy student and contrastive estimation compared to WAF2WEC?
We have experience with both, and they seem to have similar compute requirements in our case on our models that we've trained. But of course, if you scale Wave2X to these large amounts of data, which I don't know, we don't know yet if university student scales to this amount of data, like the 50,000 hours of there. Of course, the compute is the required compute is huge, and also the models that were used there were bigger, so their Wave2X for these, I mean, for these remarkable results, you need quite a lot of compute. And I think I haven't the numbers yet right now in my mind, but this requires a strong machine.
Yeah, so in the case of noisy student training, each generation was trained on 128 cloud TPUs for 1 to 3 days. And that's per generation, so it's a lot of computation.
Yes.
Okay, so WAF2WEC is not really that more expensive than the other approaches, I guess.
No, actually.
Okay. Thanks.
Thank you. Another question?
Well, I have another one. If no one
Yes,
else
please. Yes.
is.
Yes, come on down. Yeah.
So it seems to me that it would be kind of beneficial to combine the noisy student with the contrastive approach. Do you know if this has been tried?
Yes, this has been tried, I think, last year, and they achieved, I think, state of the art on the LibriSpeech benchmark, like on the actual LibriSpeech, by combining both methods and using like huge amounts of data and computation as well.
Yeah. Okay.
But I'm not sure if it has been used like in a low resource setting. I think they used the complete LibriSpeech, which means like 1,000 of labeled hours, and as well for common voice some data, I think.
Yes.
Okay.
It was actually trained on this 50,000 hours of data.
Okay.
If I recall correctly. Yeah.
Okay, thank you.
Thank you. Further question?
Yeah, this is David. I'm sorry, my laptop is weirdly connected,
David.
so my camera doesn't work for the moment. You say that there is plenty of data available out there. Do you know if we can just, from a legal perspective, use whatever we can download to train our models?
No, I don't know. I'm not.
We don't know yet.
Yeah.
But just that there are the possibilities. Maybe there are chances for collaborations also, like with such radio programs or TV shows or parliaments. I mean, we also have created a labeled data set. We have to create a labeled corpus that we presented at this conference this year, where we collaborate with Swiss parliaments to create a labeled data set of around 300 hours of labeled speech text data. So there's definitely room for such collaborations, we think.
Okay, thank you.
Okay, thank you. Maybe I have a question on the presentation models that you have presented. Is it possible to combine many models, whether, for example, you have contrastive model, and then you have another model that you see that is relevant? Is it possible to combine many models at the same time or in cascade?
So yeah, with the contrastive loss, I think it's kind of easy because, for example, Wave2Vec gives you the pre-trained model, and you can just use it as a like pre-processing step for the audio input, and then use the result of that for the training of another OSR system. which means that you are not going to train both at the same time, but you can combine them. And I think, yeah, you can also train them at the same time, but then it's a little bit more complicated to integrate.
Yes. Okay, thank you. Yes.
When will you finally apply that to Swiss German?
When we have a GPU available.
What you have? Just one.
Ideally 128.
So I have another technical question. I was a bit surprised that you said when you do fine tuning on the downstream task, you only learn or update like the linear projection. And I mean, for language models like, I don't know, BERT and so on, you basically, when you fine tune, you update all the weights. So why don't you do that for these speech recognition systems?
Good question. Yeah, I think this is a empirical. There was an empirical insight from paper authors. So that in this case, freezing the weights is the better way to go. I guess it could also be related to that they trained on a very similar, pre-trained on very similar data as they fine-tuned. So it was both LibriSpeech. So maybe this was one addition, point that made it easier for them to just freeze the weights. And yeah, but of course, if in practice, maybe you have to try both, freeze or fine tune them.
Okay, thanks.
Thank you. I think that we are done with this session. I'd like to address my thanks to Pius on his presentation on GPT-3, and of the team, Lukas, Christian, and his team for the semi-supervised machine learning for speech recognition on German Swiss. And I would like to thank you all for your interest in this session, and see you in the next sessions.